If you remember, last time we were lecturing, we were talking about how easy this unit is, right? And we're still using all those uniform acceleration equations. But instead of throwing like straight up, we are now throwing like at an angle, right? Some angle. And so what did we have to do? Well, we had to resolve that velocity, right, into velocities going over Vx and a velocity going up Vy, correct? And we could do the normal math problems like always. And if I want to find out, so this is going to come up like this. And so far, we've been talking about shooting and landing on the exact same horizontal plane. If I want to figure out how high up in the air this gets, that marker's completely gone. How about this one? Okay, I want to find out how high in the air that gets. Which one of these velocities do I use as my initial velocity? I use Vy, remember? That was the only difference, really. I can still figure out, I can do Vf up at the top is 0, but my Vi is going to be this initial velocity. I can figure out how high it goes in the air. If I wanted to find out how much time it takes to get all the way and back down, which velocity do I use? Same one, right? If I throw something up in the air and I want to figure out how long it takes to get up and all the way back down, I still use this as my initial velocity. When's the only time I have to use this?
Calculating how far away to land.
At the end, I want to figure out how far over it lands, right? So I use this to figure out how high in the air it went. I use this to figure out the time of flight. Once I had the time of flight, I could take the time of flight times the Vx, and that'll tell me how far over it lands. Remember all that? Kind of? It's been a while. Okay? And so we did a lot of those things, played around with them. And then what I was interested in doing is, you know, if I want to find the range of something shooting at an angle, you know, what did I have to do? The whole step was, well, figure out what Vy and Vx was. That was the first thing you had to do, right? And I take Vy and I figure out how long it's in the air. Once I have that time, I took it times the Vx to get my range. That was a whole bunch of steps. And I didn't want to do that. I wanted, if someone on the test gives me the velocity of the pumpkin and the angle that I'm shooting it at, that's all I wanted to know. I want to be able to figure out range just from those two variables only, right? And you know, you can do this in physics. You can take a whole bunch of steps that you did to solve a problem and just put them all in there with the variables, algebra, and come up with an overall equation that would do it, right? And that's what we did. And so we got an equation for range. We started, you know, with Vx times time, but we didn't want either of those, so we did substitutions, right? And we got range equals, and there was a minus sign, but we're leaving that off, right? Because we're going to put 9.81 in for gravity instead of negative 9.1, so we're just going to leave the negatives off, okay? So range was v squared over g times the sine of twice the angle. Okay, so this was the equation we used, and the important part about this equation is it's only for shooting and landing on the same plane. And the other thing is, sometimes I'm not sure I really want to give it to you, because once I give it to you, now you kind of forget the actual easy math and all those steps, because you just plug it in for here and you just stop, you know, figuring out how we actually got it, you know. So that's always a danger on deriving our own kind of cool physics equations that we can use. So this will only work in shooting and landing on the same plane. And there's really interesting things about this. This thing tells us that the maximum, the best optimal angle for the farthest distance you could throw something is what? 45 degrees, because 45 times 2 is 90, and the sine of 90 is 1, a maximum, right? 1. So this equation, you could write R max is just v squared over g. If you take your velocity and square it and divide by gravity, that's how far you'll be able to throw it. That's the maximum distance you'll be able to throw it if you go at 45 degrees. Okay? The other interesting thing about this equation was there's always two angles that give you the same range. You could pick two different angles. And how are those angles related? They add up to 90, and the math term for that is a fancy mathematical term for adding up to 90 is complementary. Complementary angles will give you the exact same distance. So I could shoot, you know, I could shoot at 30 degrees and it would come like here. I could shoot at 60 degrees and it would also go there. Okay. Now, you know, the one, which one of these would be in the, which one of these would get to the target first? The 30 degrees. It's not going to be in the air very long at all, right? It's definitely not going very high. And the reason it's not being in the air for a long time or going very high is because its Vy is small, right? Its Vy is a lot smaller than the one for 60 degrees. The one for 60 degrees, the Vy is huge. So it's going to go way high in the air. It's going to be in the air a long time, okay? Now, the one for 60 degrees, its Vx is small, right? So how does it get all the way over here? Well, it was in the air for a long time, right? So you take the big time times a small Vx, you get this range. And then for this one, you take a really big Vx times a small amount of time, and you get the exact same range. That's how it balances itself out, right? So complementary angles will give you the same range. Okay, are we good on that review? Okay. So what we're going to focus on today is not landing on the same range. So this is like a lot of different sports. So I'm going to shoot at basket. You know, I'm going to launch here, but I'm going to try to launch into a basket up here. See? So there's your horizontal line, and we're going to end up somewhere not on the same plane, right? So I have from here over to there, I have what we call the range. That's the horizontal displacement. From here up to here, I have a vertical displacement. And because we're doing projectile motion and we don't use D anymore, we use R for the range. And anybody know what letter we use for vertical?
I don't know why.
It's very close to R. S.
Hey.
We actually use S for displacement in the vertical direction. Okay. Now, by the way, this situation is what so we have an angle, right? And we have, you know, Vx. We got Vy. Okay, this situation would be called an elevated target. The target is above where we're shooting from, right? That's like playing basketball or something. And so the S is a plus. You put in a plus S because we're measuring out. You could have another situation. You could be like I'll do something like this, and I'm throwing this way, and it, you know, comes down and lands here. Okay, this is called an elevated launcher because the launcher is above the target, right? I can still take this all the way out and then go down. And so this is going to be a negative S down. Okay. So what I want to do, and so all the equations still apply. If you want to find out where it is at any point, you still use these. You still use your, you know, D equals VIT plus 1 FAT squared, and your VF squared equals VI squared. You still do everything to figure out where anything is, okay? But what I want to do with this equation is, and what we normally did, we're not going to do it now. We go out here in this, above the PAC. I have a little tiny cannon that I can clamp to a table that you can, you know, spring load a little yellow marble thing. And you can pull it and it'll launch, okay? And it launches the same, basically the same velocity, 7 meters per second, like every time, okay? I also have a little basketball hoop I made, and I would take it out a certain, we divide you up into teams. I take the basketball hoop out a certain distance away, and I would either put it way up here for an elevated target system, or I'd put it way down below for an elevated launcher system. And your team would have, like, you know, 10 minutes to come here and to put the cannon at a correct angle and launch it so that it goes right in the bucket. Okay, that's what we used to do. It was really fun because it would work. And you'd be like, physics is real, you know, and it was great. Okay, we're going to use an online applet instead now. But what we would do is we would try to derive a really nasty equation that has R, S, V, and then the angle, because we wanted to solve for the angle. So you'd go out there and I'd give you a tape measure, and you would literally measure across. You have to be really accurate with your measuring. you'd measure the range over to the vertical line of the target. That'd be your R. And then you'd measure either down to the target or up to the target from that line, right? And that'd be a plus S or a minus S. And then I told you the velocity of the bullet coming out of the cannon. So you have R, S, and V. Okay? And you have to solve for the angle. There's two angles again. There's two angles for this. However, they're not complementary. They're not related. And you have to actually figure out both angles. You can't just figure out one and then know the other one automatically. You got to figure them both out. Okay? So we want to derive, that's what we want to do today. We want to derive an equation that has all four of these variables in it. No Vy, no Vx, no time. Okay, we want just these three. So I can plug these three in and get the angle. The two possible angles. The reason this is difficult is because whenever you are shooting and landing on the same plane, your S is 0, right? Your vertical displacement is 0. And so this particular equation, remember this equation? When you solve for time on this, if your D, your S right here is not 0, which means you're not shooting and landing on the same plane, like you're either above or you're below. When this is not 0, this is not fun to solve for time. It's a quadratic, right? T squared, time, and a constant. If we shoot and land on the same plane, our displacement is 0. I can divide the whole thing by time, and I get like VI plus 1/2 AT, and that's easy to solve for time, right? So this derivation isn't going to come out pretty because it's going to be a quadratic. That's what's going to happen. Okay? All right, are you ready?
Sure.
Okay. This is one of those derivations that doesn't actually take too long, but normally you're waiting for it to be really pretty and nice and simplified. And this one doesn't do that. This one turns out to be a very ugly looking thing at the end. Okay? But never fear. It's gonna be great. Okay, so let's say now we're shooting like this, and we're gonna shoot up to here. Okay, and we have a plus S, and we have a range, and we have an angle, and we have a Vx. This is a Vy. Okay, because here's our velocity coming out of there. And I want to get an equation that has all those things in it. V, S, R, and then the angle. Okay? So there's a couple equations I can start with. What's the equation for the range, the horizontal range? That is a pretty easy equation. Range equals what?
VXT.
Yeah, it's going to be the horizontal velocity, right?
Yeah.
Times whatever time you are in the air.
Yeah.
Everybody remember that now? Yeah, that was the easier one. Now I'm going to ask a harder one, which is still fairly easy. What's the equation to figure out how high up in the air this would go? So my D is actually S, right? And then so VIT, initial velocity times time. What's the initial velocity going up?
VY.
It's VY, right? So VY times T, right?
Yeah.
Plus 1/2. What's acceleration? Gravity. Times T squared. Right? Okay. So these are my two equations that I can use to start this derivation. There's an R, there's an S. I don't have the V in there anywhere yet. I don't have the theta in there anywhere yet. So I'm going to have to, fix that. So let's start with this one here, because what I want to do is I want to solve this for time and then plug it in this one, right? Because I don't want time in this equation. So that's pretty easy. Time is R over, do you know what Vx is?
It's the cosine of, it's V cosine of the angle.
V cosine of the angle, right? So V cosine of the angle. Okay, and I'm going to put this time in for these two times right here. Okay, so here we go. S equals, now the first thing I have is a Vy, but I don't want Vy in the equation either. So what can I put instead of Vy? V sine of theta. So V sine of theta, that's great, right? Because angle and V, I need those in the equation, right? And then for T, I'm going to put R over V cosine theta. plus, I'll just do G over 2 times this squared, okay, T squared. So that'd be R squared, right? Over V squared, right? You got to square every one of these things, right? And cosine squared theta, right? Everybody remember how to write that? That's saying you take cosine theta and you square the whole thing, right? It's not saying you don't square the angle and then take the cosine of that, right? So we put the squared like on the cosine, not on the angle. Okay, so let's see what we got. We have S equals, so this first part here is nice. There's a V on the top and a V on the bottom. They cancel, right? So I'm left with an R. And then I have sine over cosine. Tangent. Everybody know that trig identity, right? It's an easier one. Sine over cosine. So R tangent. Plus, so here I'm gonna rearrange this a little bit just so I can show you something. I'm gonna do GR squared over 2V squared times, and what's left? 1 over cosine squared theta.
That's secant.
That is secant squared theta, but that's not the trig identity I want.
Okay, cosine
What
of
is
negative
it?
first power.
Tangent squared theta plus 1, right?
Oh,
But that's what it is, and so that's what we're going to use, and you're not going to be tested on that part. So instead of that, I'm going to put in tangent squared theta plus 1. See, I want all my trig identities to be the same thing, and here they're all going to be tangent thetas, right? Okay, so I have S equals R tangent theta.
doesn't really matter.
So I'm going to multiply this by tangent squared theta. So that's GR squared over 2V squared times tangent squared theta. Plus, and I'm going to distribute this over the 1, right? So that's GR squared over 2V squared. I just distributed this thing through both of those, right? So what I can do here is I can take the S to the other side. So I'm going to subtract S over here, and I'm going to make this be a 0. Cool, you did. So I'm going to multiply this whole side by 2V squared over GR squared, the inverse of this thing right here. Now I'm multiplying it by the other side also, right? I mean, I'm doing math correctly, but times 0 is still 0, right? So I don't really have to show I'm doing it on the other side, I hope. Okay, so 0 equals, and I'm going to go ahead and put this term first. That's the way it properly should be written. So what do I write? So I take this, I take it times this, this thing's being multiplied by this whole thing. So I take this term and I multiply it by this term, and what do I get? Yep, tangent squared theta. There's my first term. Okay, now I'm going to do this one. So plus, I'm going to take 2V squared over GR squared times R tangent theta.
2V squared R tangent theta divided by GR.
2V squared over GR, just R, right? Because that R and one of these R squareds would cancel, right?
He said that.
And then tangent theta. Okay? Okay. Plus, this term times this term is 1. Minus, and then this term times S, all I have to do is stick an S in there, right? Over GR squared. And keep in mind, this, I've seen mistakes here. This is not 1 minus this all over GR squared. This is 1 minus this fraction. Make sure you have it that way. Okay. So there it is. It looks bad. It's not a really pretty equation. So A is 1. I mean, that's why we did it, so that really we don't have to worry about the A. All over 2. Nope, it's just all over 2. That's how the song ends now.
Oh, you're right.
We shortened the song, right?
That's funny.
Yeah, that's why we did it. B equals 2V squared over GR, and C equals 1 minus 2SV squared over GR squared. So if you were out there in our physics basketball game, and I already told you the velocity is like 7, you'd plug in 7 for the V's, You would measure how far over the target is, and you'd put that in for your R's. You'd measure how far up or down the target is. If it's up, you'd put in if it's up half a meter, you'd put in like plus 0.5. But if it's down half a meter, you'd put in a negative 0.5. There's a thing we can mess up sometimes. If the target's lower than the launcher, you're going to have to put in a negative for your S. Okay? You get 3 numbers, A, B, and C. You put those all into the quadratic formula, you get 2 answers. You take inverse tangent of both of those to figure out your angles. Okay? So you have that equation on your sheet. If I give you on the problem on an ELAB or the test, and you're going to get one, this says we're shooting at this meters per second. The target's this far away, and the target is this high in the air or this far down below the ground. What are the 2 possible angles that'll work? Okay, you'll solve for A, B, and C. You put it in the quadratic formula. You'll get your 2 answers. Take inverse tangent. Or we can program our computers to accept the range, the S, and the V. It'll say, what's the range? You type it in. What's the S? You type it in. What's the V? You type it in. Execute, and it'll just tell you your 2 angles. Right? That's what we're going to try to do today. Didn't solve my problem. Make sure you're in degrees. I did the whole thing, and I was in radians. The thing I yell at people all the time about. So make sure you're in degrees. I've already fixed that. And here we go. We're going to try to see if we can do this. So the first thing you do is you click the program button, PRGM. You should find a program button. Okay, I'm going to go over and I'm going to select new. And then it says click 1 to create new. So I'm going to click 1. Okay, everybody with me so far? Okay, it says a name. So you can name your program. So I'm going to name it like launch. Okay. Let's see here. Second alpha, we'll put the A lock on, won't it? And then L, A, U, N, C, H. Here's the name of the program. I'm going to click enter. And click program again. Click program. And then you'll see across the top, there's the second one over, so go over 1. I/O, computer programmers, what's that stand for? Input, output, right? So there's several things here now, okay? So we are gonna click number 2 for prompt. And then it says prompt, and it says, you know, what do you wanna prompt them to do it? We can actually do all these, we can do as many prompts as we want and separate them by commas. So I'm going to do alpha V. I want the velocity, and then I'm going to hit the comma, and then I'll do alpha. Let's put in the range next, and then I'll do a comma, and then alpha S. There's S. There's S. Okay. And so what happens when we execute the program later, it'll have a V question mark, and you type it. And then as soon as you enter it, it'll say R question mark, and you enter that. All right, that's how that works. It's computer entering. Okay, so I'm going to click enter. Okay, and now what I'm going to do is I'm going to start doing some math. Okay, so I know my A is 1 already. So what I want to do is I want to solve for B. So B is 2B squared over GR, right? So I'm going to just start doing that. I'm going to do 2 times, you know, I wonder if, I think I keep using my keyboard and I should be using this thing here probably. 2 times V, so alpha V, and we're going to square that, square it, okay? Now, then we're going to divide by, and then here's where you were talking about, and the other class kind of got all off on me. They want to put a parenthesis here, and then do G times R, and then close parenthesis. And you can do that if you want. But that's the same thing as dividing by G, and then dividing again by R.
Are
That's
you
same thing.
mentally ill?
What?
Why wouldn't you use a parentheses? Are you kidding me?
Why is it more work?
I used way less stuff than you guys did.
No.
Oh yeah.
Well, why wouldn't you do a parentheses? Give me one good reason.
You go ahead and do the parentheses. Maybe your
Yeah,
program will
maybe
work
it'll
and
work.
mine won't.
All I'm saying is that mine works now.
You already did the divide, right?
Yeah.
Okay. So it's 2 times v squared, and then I'm going to divide by gravity. Now I have to put in, that's a negative 9.81, right? Okay. So it's not the minus sign, it's this sign here, right? So minus 9.81. Now, if you put a parenthesis before that, now you're going to take it times, right?
Or you can just put R.
Now, I'm going to do divide, right, by alpha R. So what am I going to do with this? I need to store this in a variable, right? So this is B, right? So I come down here and I click store, S-T-O. Okay? I'm going to do alpha B. There we go. So I just stored that in B. I do C. Here we go. We got to do C. 1 minus. Now I'm going to use a parenthesis. I'm going to put this whole next thing in a parenthesis. Yeah, this would be a good time to use it. Right? 2 times S. Where's S? Oh yeah, right after the R.
I should have made a program for the
Times V.
For the first one?
no for
Squared. Okay, this is going to bother you. Divide by negative 9.81. Also divide by R squared. And then we can close parenthesis that. There we go. And I'm going to store that, STO, in alpha C. Enter that. Okay, I have something in B, I have something in C. All right. So now what I need to do is the quadratic formula, right? A is 1, I got B stored in there, C is stored in there, and now I need the quadratic formula. I need to do that twice. Let's start with parentheses right at the beginning.
Yeah.
You guys like parentheses, right? So
Okay.
opposite. You know what? Now see, I hope that worked because I did it on the keyboard. I think it should still work. Okay. Opposite B. And let's do the plus first. And then square root, right? Where is that? That's second x squared. Square root. And it puts a parenthesis in for you. You can't even stop it. Okay, and what's in here? This is b squared. Minus, right? Minus 4. There, A is 1, so we can just skip it. Times C.
Isn't it weird how?
Okay, so now close parentheses. B squared minus 4AC, right? Okay, close parenthesis. And then
You need another parenthesis if you're gonna do all of it too.
you know what?
I think that's it.
Maybe that was it. Because all of a sudden I'm like, wait a minute, I need another. I bet you that was it.
Yeah.
No, you didn't know.
No, my program I did on my website is correct.
Okay.
I know that. The program I just did in the last class, something went terribly wrong. And that might have been where the problem is I didn't do a screenshot of that program I did. So we actually have to close this parenthesis up and then divide by 2. I don't know. I think that's what I did. I don't think that was a problem. I don't know. Okay, we'll see. All right, we're going to store that in something. I'm going to use X. alpha x, enter. Okay,
What
fine.
could you do? Is there a computation?
I don't know, there's something, I'll look it up later.
I don't
I'll figure it out.
remember.
Okay, opposite. Did I use this? I used this on the first one, didn't I? I hope I did.
I'm gonna throw this as B actually. 'cause I don't-
Alpha b, this time it's minus square root b squared minus 4, I'm still going to do my times, alpha c, close parenthesis, divide by 2, store it in, I'll use y.
I'm not done with this.
Okay, so I got my x and my y. My x and y are actually tangent of theta, though, right? Okay.
So now I have to find the inverse tangent of each one.
Okay, yep. So I'm going to do second tangent of alpha let's see, could that be? No, that's not it. Okay, close parenthesis, store it in, I'm going to use alpha 3. Look at that. That's actually a theta.
Oh, really? Alpha 3 is theta?
Yeah,
Oh, it is. Oh,
cool. Enter, and then I'm going to do inverse tangent
but now you need to find differences.
of y. Close parenthesis, store it. I'm just going to put it in z.
Yeah.
Z. Okay, enter. Excellent. Okay, the last thing we have to do is we have to display these to the screen. So I'm going to click program again, program. I'm going to go over to the input output, and I want to click 3 for display, 3. And then you can just do alpha theta, comma, and then alpha, what was my other one, z? Z. Okay? And you can click enter. And that should be it. So we're going to quit. This saves it automatically. We already tested that. So second mode is quit. And then if I want to run this, I click program. And you'll see that there's a program in there now. So I'm going to do 1 for launch, and it says program launch, and you're going to click, enter to launch, and it says V, what's your velocity? So I put in 30, enter, range 87, I think that was right, 87.1,
Yeah.
enter. Did you click the minus or the subtract button? This one, 15. Enter. I got 60 and 20.
Yeah, that's what I got.
Same.
That kind of makes no sense.
Well, hold on a minute now. That sounds about right. So I'm going to take this 60, launch. Get there, get there, get there.
No.
Boom!
Okay, well then my program's wrong. What's up?
I have no idea what we did in the last class, because I swear that's what we, you know what? I bet it's that parenthesis in that quadratic. I bet it was.
No.
Now this says if we go at 20, it was 20, right?
Me and Bo
20,
did something wrong.
20,
What
look
did
at
we do
20.
wrong?
Look at 20. Here it goes. Look at, boom, money. Physics is awesome.
I hate you. I hate you.
Well, now I'm really frustrated too, because what in the world happened in the last class? I mean, it had to be that quadratic part. I bet it was that quadratic part. And, okay, so let's just change that to what I think I had it and see, because that would
That's wrong.
ruin it.
Yeah, because you would have the square root thing, and then subtractor at it from negative b.
It would be dividing the right side by 2, not the whole thing by 2.
Yeah.
I think that, okay, so second quick.
Yep.
And then, can I just do enter?
Yeah.
And then what was it, 30, 30, what was the next one?
87.1.
87.1 and minus 15, enter. Those are what we got.
Yeah.
Those are what we got. I'm pretty sure.
Yay, solved it.
That had to be what it was.